Good evening. This is Jordan Dyer, and I will be presenting on the critical assignment preparation assignment number 1 for Kinesiology 516 ATP pathways. I'll do my best to go over diagrams that involve the breakdown of one molecule of glucose and one molecule of palmitic acid. Please bear with me on the pronunciations. I think I got most of them down, but we'll see how it goes. And I'll also go over some of the key steps of each of the pathways, the ATP yield for each of the pathways, and other characteristics involving the pathways, limitations for ATP yield production, and so on and so forth. So the diagrams I've taken are just pictures from the textbook. As you can see here, this is kind of going over an overview of a glucose breakdown. So if you're looking at one molecule of glucose, it has an ultimate yield of 34 ATP molecules. 2 of those molecules are used to phosphorylate glucose. So really it's just a net gain of 32, as you can see kind of at the top. Or on the later slide, I'll show you that right up at the top you can see some ATP is being used to phosphorylate glucose at the glycolysis section. So glucose is broken down through glycolysis, which has 2 forms. Pyruvate is produced, and that can be the end product of glycolysis, or it can also produce lactate as the end product of glycolysis. And when pyruvate is produced and produces lactate as the end product, that's considered an anaerobic and rapid glycolysis, which typically generates about 5% of the total ATP production. And if pyruvate ends up being the end product in glycolysis and continues to be broken down to acetyl CoA and then is broken down more, that is where more of the ATP is majority, the vast majority of the ATP production is carried out. So we can take a look. This is more of a closer look at glycolysis, and we'll go back. So glucose is broken down through glycolysis to pyruvate, which can continue down if it is the end product, and broken down into acetyl CoA, and then it goes through the citric acid cycle, also known as the Krebs cycle, and then ultimately going down through the electron transport chain, where oxidative phosphorylation occurs, where most of that ATP is produced. And so that other form, when the pyruvate goes through and is broken down in acetyl and goes through the Krebs cycle, and the oxidative phosphorylation, that is known as the anaerobic, that's actually known as the aerobic slower glycolysis. So like I said, glycolysis, during that process of glucose being broken down, 2 ATPs molecules are used. So technically there's a net gain. Altogether there's 34 ATP molecules that are produced, but 2 of them are used. So really it's only 32. After this whole process, it results in H2O and CO2 after going through that process. And this is a closer look at the Krebs cycle, where some more ATP is produced. So moving forward with palmitic acid, and which kind of break down. Palmitic acid is a 16-carbon saturated fatty acid, and if we're looking at the fatty acids, the breakdown of TAGs, I'll just say that and not try to pronounce that big name. So looking at the fatty acids, They are activated hormone sensitive lipase activates TAGs and to break down into glycerol or fatty acids. If you look at that diagram right there, you can see at the top. And free fatty acids are transported in the blood and then activated and broken down into acetyl-CoA in the mitochondria via beta oxidation. After that, the Krebs cycle breaks down acetyl-CoA into carbon dioxide and hydrogen atoms, and which are then oxidized via the electron transport chain involving oxidative phosphorylation. Taking a closer look at the electron transport chain, that generates a proton gradient that drives ATP production, the vast majority of ATP production. So to wrap it up, looking at some limitations of ATP production, look at muscle glycogen depletion as one of those, and also lack of oxygen regarding aerobic glycolysis. That once you don't have enough oxygen, that hinders a great deal of ATP production. All right, thank you very much.